last of the 4 lectures, and I'm going to change gears, in fact, a bit, and still remain into the field of integrability, but switch from quantum integrability, Young-Baxter type integrability, towards classical integrability, which means inverse scattering theory. So the idea is the following. Yesterday, I hope I scared you yesterday. This was the goal, to scare you with some, Bethe Ansatz, nested formulas, and so on and so on. And indeed, if you want to compute some physical observables, it's very nice to be able to compute things exactly using. So it's possible to get exact results by doing Bethe Ansatz on the microscopic model, writing formulas with this, resumming the Bethe series, getting some residue type formula, using integrable probability theory and so on. But this is quite specific, and I mean, it's a bit technical. I hope you agree with me. So today I want to show you that another approach is possible, which remains technical, but maybe which is more appealing to classical physicists. I mean, people playing with PDEs. This is going to be a lecture, of course, not a seminar, but it's based on some recent work that we did with Tomohiro Sasamoto and Hiroki Moriya from Tokyo Tech, and which has been published a few months ago. The idea is that somehow we want to quit the discrete version of the model and go to a coarse-grained, continuous PDE description of the system, and then try to solve the PDE. So I'm still trying to repeat some things that I told you before, but again, we want to see what happens if you connect a system with 2 reservoirs at different potentials, let's say electrical potentials, and we have some external field, electric field, to make it look like physics talk, which drives also the electrons. So you have a difference of potential and some field which drives the electrons inside. And indeed, we could model that by an exclusion process with particle hoppings on sites and so on. But again, a naive physicist would like to write some kind of equation for that, some kind of conduction equation for that. And mathematicians tells us that naive physicists are not totally wrong, and that indeed it's possible to do a hydrodynamic approach for this kind of problems. And it looks, again, very naive, but it's not naive at all. And the fact that for exclusion type processes, people have been able to derive rigorously the existence of a hydrodynamic limit is a kind of very great feat of mathematics and probability in the last 20 or 30 years. Many names are attached to it. I just selected a few of them, but there could be many others. Anna De Masi, Pablo Ferrari, Joel Lebowitz, Enrico Presutti, Herbert Spohn, Raghu Varadan, but also Kipnis, Landim. It's a whole school of people who worked on hydrodynamic limits since the 80s and developed methods to prove rigorously that the systems that we consider, like stochastic models on lattices, do have a coarse-grained limit under the condition of defining locally some density. So you have to make some coarse graining and say that you have a local density of particles, or xt, and you have a local current. And then by going to large space and time scaling, typically a diffusive scaling, so time diffusive scaling means that space scales like square root of time. Okay, so you put a scaling parameter, you can write a hydrodynamic equation for the evolution in time of the density inside the system. Again, for a physicist, this is quite naive, because it just tells you it's a continuity equation, that the derivative with respect to time of the density is minus the divergence of a current, and the current is given by minus d gradient rho, this is Fourier's law, okay, plus the electric field E times conductivity. So that a physicist would write it almost on the back of the envelope, but there is a lot of deep math which is involved in that. Okay, but again, this equation is a hydrodynamic equation, but it's not stochastic, it's determinist. So you have to understand it as a kind of a law of large numbers, hydrodynamic limit for your stochastic system. There are no fluctuations. Dynamical equivalent, I'm caricaturing a bit, of the perfect gas law. PV is equal to nRT is something on the averages, and it's a law which relates averages. So here you have a hydrodynamic law, which relates averages, local averages of density and current. Okay. The only thing that survives in this coarse graining procedure, in this hydrodynamic limit from the microscopic world, is the diffusion constant here, the coefficient in Fourier's law, okay, and the conductivity, sigma. These two transport coefficients have to be determined from microscopics, but if I give them to you, you don't care about the microscopic structure anymore. You can write this hydrodynamic equation. It's a PDE, and you can try to study it now, forgetting about algebraic methods, but rather going to analysis and playing with this PDE. For example, in the case of the exclusion process, D is simple, it's 1. Sigma is 2 rho, 1 minus rho. And this PDE, if you just slightly change the variables and instead of considering rho, you consider U is equal to rho and minus 1/2. So you just center rho around 1/2. This PDE becomes a very famous PDE, which is known as the Burger's equation. And of course, there are books on Burger's equations. People have studied it. So there's a lot of things you could say on this point of view, and I've completely washed out the lattice structure and the microscopic structure. It's a bit, again, I'm using metaphors, like going from the Ising model in any dimension to 5-4 theory, going to a field theory, to a continuous theory. So you're not using integrability in general when you play with 5-4, you use other methods, perturbations, whatever, okay, saddle points. Very good, but here there's no fluctuations. And in statistical physics, we want to take into account fluctuations. So the question is, how do we incorporate fluctuations into this kind of description? So very naively, and this is not totally wrong, I'm going to be more precise than that, you could say, okay, now I could do Langevin's program and add some noise to this equation. Is it correct? Is it rigorous? Is it just, hand waving? Well, it turns out to be almost correct. The thing you have to control is the coefficient of this noise that you add. And this is, in essence, the idea behind this celebrated macroscopic fluctuation theory. So this I already showed you in the first lecture, but the idea is to try to find a probabilistic description of seeing a local current J and the local density flowing through the system. And now I don't take the average values, the typical values will satisfy the hydrodynamic behavior, but I'm interested in seeing any non-typical empirical current and empirical density. So of course, the hydrodynamic behavior in the simple case of Fourier will give you a straight line for the density, but I want to see what is the probability of seeing the red line for the density. So I want to have something more than purely deterministic hydrodynamic description. And there is a large deviation law at the functional level. It was proved by Varadin, for example, for this probability distribution of these functions, which depend on space and time. And the question is that, okay, it's good that this exists, but as physicists, we would like to have some ansatz or some principle to compute this large deviation functional, this I. And fortunately, there is such principle. It was suggested and put forward by the group of Gianni Gionalazino in Rome, Lorenzo Bertini, Davide Gabrielli, Alberto da Sole, Gianni, and Landim, I forgot his name. Sorry, okay, Landim, it will come back. And their idea was, so two ways of saying it, of presenting it. You can take this as a principle, as a postulate, new law of physics. Maybe exaggerated, but okay, just take it for granted. This probability distribution is given as minus exponential of an action, and the action is given by this formula. So you have depends on the current, which is a function of x and time, on the local density, and it's a kind of quadratic action, but of course there's a division by sigma of rho. And if you really stare at it, as I told you, the hydrodynamic equation, well, I will explain that immediately after. Okay, so stare at it and memorize it. And of course, you have the relation that the continuity equation, there's no creation or destruction of particles in the bulk. So the time derivative of the density is minus the divergence of the current. So there's a kind of Boltzmann principle out of equilibrium. I'm not supposing any equilibrium here, but of course there are some hypotheses. It's only valid for diffusive systems. If you have a ballistic system, it will not work. There are some proposals for extending it, but it's not completely finished yet. So it's for diffusive systems. So for example, in our example of the AZEP, it will work for ZEP. It will work for weakly asymmetric exclusion process, but not for TAZEP. Okay. So if you have a weak asymmetry, it works because it's still diffusive. But if you have a strong asymmetry, or TAZEP, which is totally asymmetric, it will not work. So you need to change this action. Now, so you have this kind of large deviation a la Boltzmann principle. And suppose you want to solve some problem. I want to compute the probability to have a current like that, or doing something like that, or some density profile like that. Then the idea, which is also everywhere in statistical mechanics, is that you don't really need to scan through the distribution very precisely. If you want to, very often, there is one dominant phenomenon, one dominant probability, which is much bigger than the others. So typically, to solve some given problem, and I will give you a few examples during the talk, only the dominant, because it's exponentially rare, so there's only one which dominates. So it's really an optimal path problem, an optimal fluctuation problem. And what you have to find is the optimum of this action, and this will dominate the statistics because it's exponentially more probable than the others. Okay. So somehow, even if you look at rare events are rare, but they are produced by one special occurrence, history, which is exponentially less rare than the others. So this one is itself very rare, but the other ones are much rarer. Okay. You're used to that from StatMech. It's always like that in StatMech. So what we have to do now, if you think about it, we are back to very classical physics. We have an optimization problem with an action, and we can just turn the machinery to try to analyze that. Not so easy, you will see, but at least this will not frighten a normal physicist, because he or she learns about Lagrangians and actions from second year of university. The daily bread and butter that we play with, optimizing something.
But that dominant path then satisfies the generalized Berger.
So the dominant path, no, because what satisfies the Berger, oh, yes, I mean, yes and no. You're right, this would be true in the bulk in some way, but now I will try to impose some conditions on the history I want to look at. And this one will not satisfy the Berger's equation. What satisfies the Berger's equation is somehow the absolute dominant, which will give you 0 here. Action is 0. But now I will impose some conditions. For example, I want to see some value of the current, and this will select among all possible paths a subclass on which I will have to optimize this action. Yeah, thank you for your question. I will answer this question in the next slide. Indeed, you had here before the hydrodynamic equation. In the hydrodynamic equation, there is no probability. It's a deterministic equation. Okay. And as I told you, you can reconstruct this action for the MFT, or you can understand it in a kind of heuristic way by saying that, in fact, instead of writing the equation that I just wrote before, which would be the same as that one, for getting over the external field, and removing the external field. I'm totally symmetric now. You add a noise term, but the amplitude of the noise depends on the conductivity. So if you do that in a kind of formal way, I think in a naive way, adding the noise term would be quite natural. You add fluctuations. So the little important ingredient is to understand what is the amplitude of the noise that you add. And if you adjust the amplitude like that, then you have a stochastic differential equation, PDE. And whenever you have a stochastic PDE, you can write a path integral. And if you write a path integral, it's precisely the one which I showed you before. So that's another way of understanding the same thing. The point is that the group of Rome, they are mathematical physicists, so they really prefer to present things like that. One deep reason is that if I write this stochastic PDE, it is a bit like KPZ, it's not well defined. So immediately you're opening, again, the Pandora box, and you say that, no, this has no meaning. You have to do something like Herrer's program on this equation, so you cannot start from that. But again, for heuristics, it's very nice. And as I told you, there are only two unknown coefficients, d and sigma, which necessarily come from microscopic physics. You cannot get them for free. So there you have to work on microscopic physics. But it's usually much easier to get them. Simple formulas, you can almost guess where they come from for the Z case, and you don't need to solve complicated things. In the first lecture, I alluded to this Onsager-Markov functional. Maybe you remember I was talking about the Hessian of the entropy and the Onsager response matrix, which was symmetric. And I told you that in the 50s, Onsager and Markov devised a theory to understand fluctuations at equilibrium. Okay. Well, MFT is a nonlinear generalization of Onsager-Markov far from equilibrium. And if you again go closer to equilibrium and specialize their postulate of the Romans, you get back Onsager-Markov. So things fit well together. Any question about that? What?
You justify the square root, or just?
No, you can justify it by using, so it's local equilibrium hypothesis, by using a kind of Einstein relation. It's exactly, in fact, Einstein relation where it comes from. So of course, I mean, you have to put things, space them, but yeah, you can hand-wavingly justify it, understand it. So a naive physicist would add the noise. A good physicist or very good physicist like the Roman people would add the square root of sigma. Okay. By the way, Gianni Giannalazzino is also the famous particle physicist. Nambu Giannalazzino, he's the same person. But he went to more interesting things. StatMech is much more interesting than Higgs boson or whatever. Anyway, so now we can really turn the manivelle, I don't know how you say that in English, the machinery, and you have an action to optimize. So you can write Euler-Lagrange equations. Okay. Euler-Lagrange equations is with the Lagrangian, but we know that whenever we have Euler-Lagrange, we can try to do a Legendre transform and go to Hamiltonian dynamics. I will not do it. I will just give the result. It's a bit longish, but it's rather straightforward. So we have Euler-Lagrange equations for rho and j. Okay. And going to Legendre transform and going to Hamiltonian formulation, we keep rho. Rho is like x or q, and j is like the speed. So now you have to move to momentum. So the momentum is h, and rho and h are the Hamilton variables for your dynamics. So h is not the Hamiltonian, h is rather like the momentum. Sorry for these notations, but they are the typical notations in the field. Anyway, so you can write the set of Hamilton equations for fields, the fields rho and the field h. So rho is really the density field. H is the conjugate field to the current. It's a kind of, in fact, technically, it's a dupe conditioning for people who know what it is. In probability, it's really a field that conditions the current to behave the way you wish to. So you have nice PDEs which are coupled. You have an underlying Hamiltonian. So this is classical field theory. Okay, very reassuring, but not so much, because if you look at these equations, for example, there's a minus here in front of the diffusive term. So it means that there is a danger of blowing up. It's not so standard. But anyway, you can try to put these equations and study them by different means. And if you can study them with some boundary condition that occur in the problem you're studying, you can in principle compute the large deviations directly at the macroscopic level without having to go into the microscopic problem and using integrability at the microscopic level to get the results that we got yesterday, for example. But this is a kind of program, and up to very recently, it was not possible to in fact do it, because these equations are quite hard to solve. So I wrote them again. These equations, they should contain the physics at macroscopic scale. So they should contain the shocks, I mean, whatever you want to try to compute at macroscopic scale once you have coarse-grained enough, but they are difficult. I mean, they are difficult. There is a problem of well-posedness, as I told you here. There's a kind of blow-up danger. The boundary conditions that will come, and I will talk about them, they are going to be non-local. So it's not a Cauchy problem. It's a problem which is, and it's not even a Sturm-Liouville problem. It's a kind of mixed boundary problem with some bizarre boundary conditions. 10, 15 years ago, Thierry Bodino and Bernard Derrida found some stationary solutions. So this equal to 0. Makes things, as you see, there is a dx in 1D. And then things can be computable. And this allowed them to define something called the additivity principle. But then the Rome group and also themselves, they showed that there could be some linear instability, and this stationary solution could be linearly unstable, so no physical for your equations. So stationary or additivity principle doesn't tell everything. Time-dependent equations were only solved for free Brownian motions, but then you don't need all this machinery. If you have free Brownian motions, you have free Brownian motions. But anyway, it's already a check that these equations are not totally wrong. They give back results for free Brownian motions, which is not totally trivial. Many people, starting from Paul Krapinski and Baruch Merson in Jerusalem, Paul in Boston, did some perturbative analysis of these equations. There's a small parameter, which is in fact some, which again will come, which is a Laplace parameter. If this parameter is 0, you can solve the equations. If it's small, you can do perturbative analysis for first order, second order, third order. But as I told you, for many years, these equations just remained as a kind of beautiful set of equations. And non-trivial results for this macroscopic theory of fluctuations only came from, bizarrely, solving exactly things at the microscopic level, doing a continuous limit, large L limit, large time limit, extracting some continuous formulas, plugging them into the equations, and checking that it works. It's very indirect. Okay, like what I showed you yesterday, we had some formulas for these large deviation functions, for this freedom determinant, and so on. So once you extract the large deviation function from this tool, you can try to check if it satisfies these equations. And it was not even enough because, in fact, Bethe Ansatz gives you access to the final result, which is a large deviation function, but you cannot really compute the variables rho and h from it. But okay, it was a kind of indirect check you can do. But no analytic and time-dependent solutions of these coupled PDEs were known until recently. And that's the thing I want to explain today, how you can try to solve these equations for the exclusion process. Before that, I need to, this is a course, so I need to teach you something. Unless you all know about it, I know there are some people who know it very, very well. I want to tell you about something which has a priori nothing to do for the moment. It's a kind of chapter, which is called scattering and inverse scattering. If absolutely everybody knows about scattering and inverse scattering, I don't do it. If there is a single person, Sylvie se dévoue. Merci. I have not typed that for in vain. So, okay, so forget about these equations for a moment. We shall solve them using some method which is called scattering or inverse scattering. And I'm going to tell you what it is about. So we all studied 1D potentials in quantum mechanics, square potential and so on, and we all scattered waves on it. So you have an incoming wave from the left, a part of it is reflected, a part of it is transmitted, and at least we all solved, even the mathematicians. They had to solve in their first year of university the square root potential, the square potential in quantum mechanics. Okay, we did that. Maybe you forgot, but we all did that. So we computed this reflection coefficient, and even if you forget about quantum mechanics, this is very natural. I mean, it's shed light, some part is transmitted, some part is. Typically, you apply that to the Schrödinger equation. You have a potential in blue, you send an incoming exponential ikx wave, and you look on the transmission and the reflection coefficients. And in fact, you can do it, if the potential is not symmetric, you can do it from the right or from the left. Okay, you can send from here and get reflection. So you can compute 4 coefficients. You know, reflection from the right, transmission from the right, reflection from the left, transmission from the left. So in some books, they're called R and T, but there's a kind of notation in this subfield. You call it A, B, A bar, and B bar. These are the 4 coefficients that tells you how a potential scatters a plane wave. Okay, so that's how it works. And again, exercise, this is kind of classical. Now comes the beautiful thing. So you have this potential in blue, and of course, the value of the reflection and the transmission coefficient, they depend on the shape of the potential. They depend on the potential. So somehow some information about the potential is encoded in these reflection and transmission coefficients. The great thing is that essentially all the information is encoded. If you, again, you have to take this with a grain of salt, but if you scatter any type of wave with any wave vector k through your potential, and you're able to compute how this wave scatters and is transmitted through your potential, you can reconstruct by an inverse problem the shape of your potential. Okay, so that's the inverse scattering problem. You can retrieve your potential by solving a linear integral equation, which was found by Gelfand, Marchenko, and Levitan, GLM equations. So knowing A bar, B, and B bar, there's a formula, there's an equation, a linear integral equation, in fact, 2 equations, which are coupled, but linear, which allow you to reconstruct the shape of the potential. This is a bit like Fourier transform. If I give you the Fourier coefficients, you're able to reconstruct, in principle, your function in real space. So it's kind of elaborate Fourier transform. So now let's take an example, which is a typical example for which this method was invented in the 70s by Lax, Kruskal, Miura, many people. I mean, Newell, Ablowitz, whole group of people, applied mathematicians who worked on that field in the 70s, and some of them still very active. So they played with this KdV equation. So it's not the MFD equation, it's a KdV equation. And this equation has some properties. It has an infinite number of conserved quantities. It has some solitons, solitary waves that scatter and so on. And suppose you want to solve this equation with some initial condition. It's a hard problem. It's nonlinear, 3rd order. How do you solve that? And these founding fathers and mothers of the inverse scattering theory give us a recipe to solve this equation with a given initial condition, u of x. It's kind of mind-blowing. Remember, the first time I heard about it, I didn't learn about it, but the teacher in quantum mechanics just told us the story. It's quite mind-blowing if you've never seen it. To solve this equation, so you need to solve this equation with time. You have a Cauchy problem, initial time, and you want to compute u at time t. So what you do is you take the initial condition, this u of x, and you plug it into a Schrödinger potential equation. You consider it as a potential in a Schrödinger equation. And then you solve the quantum mechanical problem with this potential. You scatter through this potential, and you compute A bar, A, B, and A bar, B bar at time 0 for this potential. Okay, a priori, this has nothing to do with my KdV. I just consider the initial condition as a potential in an associated equation, Schrödinger equation. But then you could also consider the Schrödinger equation with the solution of KdV at time t, uxt. This would be a different shape because u evolves with time. And this would be a different scattering problem. A priori, you don't know how to solve the problem, so you don't know what is the value of this potential. If you knew the value of uxt, it means that you can solve KdV. Are you with me? Okay. And the miracle is that even if you don't know what is uxt, you know the scattering data which is associated with it. This is the absolute miracle of this method, is that without even knowing the shape of uxt, you know the scattering amplitudes as simple functions of the initial scattering amplitudes. In fact, they evolve in a rather trivial way. The scattering amplitudes A and A bar do not change, and the scattering amplitudes B and B bar just take off a phase. What happens, in other words, is that the A scattering amplitudes are the action variables of your Hamiltonian problem underlying KdV, and the B are the angle variables we just term with the phase of your KdV equation. And this is proven directly without solving the problem by a kind of abstract algebraic method due to lax, which is a lax pair. We shall come to it in the case of our MFT problem. So the thing is that even though you're not able to solve the KdV equation, you know it through the scattering data at any time. If you're able to compute the initial scattering data, if your initial condition is nice enough that you can compute the initial scattering data, then you can deduce the scattering data at any time. And then by inverse scattering, Gelfand, Leviton, Marchenko, you could in principle reconstruct the shape of the potential of your effective Schrödinger equation at any time, but this shape of the potential is precisely the solution of KdV at time t.
When you have any PDE that you look at, is there a way to know if such a method would work?
So that's absolutely a perfect question. This is the same question as knowing, not the same, but a similar question. If I give you a microscopic model, do you know if it's integrable or not? So this is a theory of lax. If you can find a lax pair, for example, you are in good shape. I'll come to it. Just to say in one word, we recently found a lax pair for MFT equation for ZEP. This was the thing, so we could solve it. Yeah, we are going to do that. So yeah, so the thing is, if you can carry on this program, you can solve your KdV equation. I'm doing it for KdV because it's simpler to explain, but of course I will turn to MFT immediately. So you see it's a kind of nonlinear Fourier transform. In fact, it's very precisely a generalization of the Fourier transform. This can be proven. If you have a nonlinear equation and you turn out the nonlinearity to 0 and you go back to the heat equation that you can solve by Fourier transform, you can see that what you're doing here is exactly goes to the Fourier transform. So the idea is that you have the initial condition. By direct scattering, you get the scattering data at t equal to 0, a bar, b bar. Then you do the time evolution up to time t. You have the scattering data at time t. You do inverse scattering, you get the solution at time. If you replace the words inverse scattering by Fourier transform or by Schrödinger equation in the eigenbasis, that's what we have been doing all the time. We have the initial condition, we analyze it in the Fourier basis or in the harmonic oscillator basis for Schrödinger. We evolve each eigenstate with exponential EIT, and then we reconstruct the wave function at a given time. So it's really the same kind of scheme, but a bit harder, of course, and non-linear. So now let's come back to the solution of MFT for ZEP by inverse scattering. So now I'm being more specific about the problem I want to solve. Always the same problem, unfortunately. I'm starting on the infinite line with ZEP. I'm starting with two different densities, let's say rho plus and rho minus. I don't remember rho minus and rho plus. And I want to count how many particles have flown through my middle site between time 0 and time t. And I call this random variable Q of t. And I want to compute the large deviations of this capital Q of t, positively in this direction, negatively in that one. That's the total current that have flown through the middle site between 0 and t. And we want to know the statistics of this Q of t. Okay, so I'm just repeating things I've, of course, been talking about during the last few days. There's a large deviation principle for this Q of t. A little twist is that it's not Q of t over t, but Q of t of square root of t. That is the right scaling in the case of ZEP. So, and this was really proved rigorously a few years back by Varadan and Seturaman, that this is the right large deviation principle, and there's a square root of t here. Okay, at our stage here today, it's only a detail, but it's important to have the right scaling. We can also try to compute the characteristic function of this random variable. And this characteristic function of this random variable in the large time limit behaves like square root of t mu of lambda. Yesterday I used some e of lambda, if you remember. Today is mu of lambda. And the large deviation function phi and the cumulon generating function mu are related by Legendre transform. This is really, the usual thing. Once you play with it a few times, it becomes almost you can do it blindly. And we want to compute the current. So I told you the current is the number of particles that had flown from left to right minus those who flew from right to left. But this is a kind of microscopic description. I don't want a microscopic description. I want to say now everything at macroscopic level. But if you think about it, in fact, the current is the excess particles on the right. So you get the total current as the integral of the density on the right side at time t minus what was there. So this is the excess particles on the right side. Okay, so now everything is stated in macroscopic level. We don't have particles and so on. We just have a fluid with a density which satisfies some equation. Okay, so now if we go into the details, I'm going to skip some details, but all in all, we have to solve the MFT equations, which I wrote to you before. I'm now specializing for Z, D equal to 1 and sigma is equal to 2 rho 1 minus rho. And I have some boundary conditions. Okay, the boundary conditions are a bit unpleasant, but they express something important. This is the value of this driving field, which is conjugate to the current at the finite time. And you see here the value of lambda, which is the conjugate variable to qt, this lambda here, the same lambda appears. So this really tells you that somehow you want to force a current, what I call current is qt. We want to force a current of order of lambda with fugacity lambda. Okay, so this is embedded in this boundary condition. And the second boundary condition, again, you have to do some calculations to get it. But the way to understand it is that, in fact, you start with a system with density rho plus and rho minus on the left. But it's not deterministic. You put a particle on each side at the microscopic level. If you're on the right with priority rho plus and the empty site with 1 minus rho plus and rho minus on the left. Okay, so there are some fluctuations. Technically, it's 2 half Bernoulli measures on the right and on the left. And this gives you this kind of boundary condition. So you see the equations are already nonlinear and a bit stiff. And the boundary conditions are super bizarre because you have one boundary condition on H at final time. And here you have a mixed boundary condition at time t equal to 0, which mixes the two variables H and rho. Theta is Heaviside function, 0, 1. Okay. So that's a part of the difficulty because it's not really a Cauchy problem, something which mixes things together. And now if I'm able to solve these equations with these boundary conditions, I will get the optimal profile, the profile which is the most likely to generate a current of fugacity lambda. And if I substitute the solution into the definition of Q, in fact, this will give me the probability of occurrence of this Q. So that's the program we need to fulfill. And any question up to here? In other words, if you just want to forget about everything, we have to solve these red equations with these boundary conditions. And if we are able to do that, we can compute the large deviation function of we can solve the problem we initially wanted, the large deviation function of the current. So this boils down to a mathematical PDE problem. So I just give you a simple example before going to the real solution. So these are the equations. And you see here, sigma is 2 rho 1 minus rho. In the limit where I have a very low density of particles, very few, then sigma will become equal to 2 rho. I can neglect the rho squared term. This is a good model also. In fact, this is the model of bouncing Brownian motions. Because if there is very little density, and you look at the coarse grain level, each random walker will become a Brownian motion. And when two particles meet, they cannot cross each other. So your Brownian motion just reflect like Descartes law, Snell-Descartes law. Sorry for the British, Snell law. Okay, so you have a bunch of Brownian motions which are just reflecting each other. And that's a problem you can solve probabilistically, but you can try to solve it by MFT also. Again, it's a good template to see if it works. And then the MFT equations become simpler. although they don't look so simple, but they are indeed simpler. And the boundary conditions I didn't write, but they also become simpler. And the very nice thing is that these equations, which are a bit Burger's type and so on, they can be solved by using a canonical transformation, which was very useful when people studied the Burger equation, which is the Hopf-Kohl transformation. If you change rho and h into u and v through these change of variables, then these two blue equations decouple and they become, one becomes a heat equation for u and the anti-heat equation for v. What I mean by anti-heat is dTv is minus dxxv. And for u, it will be dTu is dxxu. So you decouple them and you get two heat equations, and that you can solve by Fourier transform. Okay, so it's very easy. It's a free model. In fact, these Brownian motions which are bouncing through each other, reflecting each other. In fact, it's as if they were not reflecting, but going through each other, and you change the labels. It's just a renumbering, like rays. So you can solve it just by kind of simple combinatorics. So now comes the heart of the thing. So unfortunately, these equations cannot be simplified by Hopf-Kohl, but through a kind of very nonlinear process. The young student, Hiroki Moriya, found a very intuitive change of variables, which reduces to Hopf-Kohl when you go to low density. And if you substitute, there are some reasons. I'm not going to go into the details, but there are in fact interesting reasons for these change variables to occur. But if you just take it and plug into the equations, MFT equations for rho and h, you get these nice looking equations for u and v. Much more symmetric. If I neglect the nonlinear term, I get two heat equations, heat and anti-heat, in fact, but you get this very symmetric pair of equations for u and v. In fact, the great miracle is that these equations are famous. They are known as the AKNS, Abovitz, Karp, Newell, Ségur equations. They are in fact a real version of the famous nonlinear Schrödinger equation, NLS. If you take, it's not the case here, but if you take u and v to be imaginary conjugate, u is equal to v star, then and you put an I here. In fact, these equations are nothing but nonlinear Schrödinger, which has been heavily studied. But these equations are good equations and they are exactly solvable, which means that they can be solved as I showed you for KdV. They are not KdV, they are different, but they can be solved by inverse scattering. They have a Lax pair, and the integrability, the classical integrability for these equations works. Is it okay up to here? So now I'm going to show you the, yes?
Is there some reason why the MFT equations are integrable in this case? I mean, the model originally was integrable in another sense.
So of course your question is more than justified. I will give you a funny answer and then a more serious one. Faith. For many years almost, I was finishing all my seminars about exact calculations on microscopic level, writing these equations and saying that we hope that they're integrable, that something is transmitted. Okay, now a more educated reason, when people were doing some perturbative calculations, some kind of simplifications which were not due to be there occurred. So there seem to be some patterns emerging. So integrability, as you can say, at experimental level was there. More deeply, I have no answer. But I still do believe that many of the models that we know how to integrate at the microscopic level could remain tractable at the coarse grain level. At least, hopefully, this is the case of Z. This is also the case for another model, which is called KMP, Kipnis, Marchero, Presutti. This is also the case of asymmetric exclusion process, weakly asymmetric. The hope is that this KPZ with weak noise is also integrable. So it seems that there is a kind of good, I don't know, help from, from above for our poor physicists that we are. or mathematician. Anyway, the other thing is that hopefully the very ugly boundary conditions that we had in this new change of variable, they become very simple. Two delta functions, one at final time and one at initial time. Everything seems to conspire again. There's a kind of good conspiracy, which makes things, I mean, I'm trying, I think you can see how happy we were when everything suddenly started to work after months of perturbative calculations, and suddenly within a few days, poop, started working. Okay, and these equations have an infinite number of constant quantities in evolution, and so on and so on. And now I'm going to show you how they can be solved by Lax pairs. So it's quite nice. So I'm going back to the kind of general theory applied to this case. So the classical integrability and the Lax pair, the zero curvature so-called condition, goes as follows. Suppose you have a 2 by 2 vector, psi, with two components, psi1 and psi2. And I write an equation for, psi depends on x and t, so psi1 xt, psi2 xt. And I write an equation for its evolution with space, ddx, and an equation for its evolution with time, ddt. And they are linear equations. Again, the relation with what I was just saying is not totally trivial for the moment. It's a kind of, aparté, slight aparté. So suppose I can write some equations like that, then you immediately tell me, no, this cannot be true. Of course, the time derivative of the first equation has to be equal to the space derivative of the second equation to be compatible. So if I do that for this u and v, I take the time derivative of the first one. Everything depends on time, so I have to do Leibniz rule. Here I take the space derivative, Leibniz rule. You see that these two equations will be compatible if this so-called zero curvature condition is satisfied. By the way, the word zero curvature comes from differential geometry. It's really, in fact, zero curvature when you have a curved space and you evolve in one direction on the sphere along longitude or along latitude, and you do it along latitude first and longitude then because of the curvature of the sphere, you have a small mismatch of your small vectors and you have non-zero curvature. If you do it on the cylinder, you will close the rectangle. If you do it on the plane, so the presence of curvature is precisely when this thing is non-zero, when the two Schonn vector fields do not close up. So that's really this condition, but we don't care about differential geometry, just compatibility of these two equations. Okay. Well, maybe you care. Okay, so now suppose I take U to be given by this blue matrix and V given by this matrix, which contains a wave vector or spectral parameter K and two functions U and V, which are a priori arbitrary. Okay. And I plug, so I do my calculation, I take the time derivative of this one, the space derivative of this one, I take the commutator of this one, and I plug into this condition. You will see that this condition is fulfilled, is satisfied if and only if small u and small v satisfy akin. So the fact that small u and small v satisfy akin ensures you that this system of space and time equation for capital psi are compatible with zero curvature, even only if. Okay. So it means that equation is what we call the existence of a Lax pair. So you have that. Well, you can now focus on the scattering problem. If you look at it now, linear problems. For example, if you something, something, it's just a linear. So Dirac problem, Schrödinger, in one dimension. Able to do the scattering process at a given time, then you can reconstruct the scattering data at any other time and reconstruct the solution at any other time. Just like I showed you for KDV, the same kind of machine, the same machine works. So what you have to do is to solve this scattering problem. for these two components, psi1 and psi2. And what happens is that the U and V potentials vanish at infinity. We don't know how to prove it, but we know it's true, so we assume it. Okay. But they're localized, it should be okay. And then it means that in the large X limit, well, you have a diagonal trivial scattering problem. You have plane waves. So you can really do the work. I'm sending a plane wave at minus infinity. So there are two types of plane waves, first component and second component. It gets scattered at plus infinity with some scattering coefficients, which are the scattering data. And here appear the A bar, B bar, that generalize a little what I told you about KdV and Schrödinger. It's exactly the same thing. And if you are able to compute this A bar, B bar, you can make them evolve through time and reconstruct the potentials U and V at any time. There's a little difficulty here. If you remember, the boundary conditions are mixed. It's not that I know U and V at t equal to 0, both of them, and I can try to evolve. In fact, I know one of them at t equal to 0 and the other one at final time. But it doesn't really matter. You can carry out the program. And the key thing is that indeed the scattering data has a trivial evolution. And they are the action angle variables of your Hamiltonian system. The system I wrote before, AKNS, is Hamiltonian, and these are the good variables. So the key feature is that the dynamics is complicated for the potential, but very simple for their scattering data. So it diagonalizes the dynamics, it trivializes it. And once you know the scattering data, JLM, Gelfand-Levitan-Marchenko, should allow you to reconstruct the potentials. Well, in fact, here it's much simpler. We don't even need to do that. And I'm going to finish soon, I hope. So we know the initial value of U, but not the initial value of V. We know the final value of V, but we don't know the final value of U. So it's a kind of mixed boundary condition. So we can carry out the scattering because there's a delta function by some pasting, very elementary calculations, which go back again by this scattering by the square potential that we learned in first year of university, not more difficult than that. So we can compute implicitly the scattering amplitudes A bar, B bar in terms of the unknown initial value of V and unknown final value of U. So what we do is we do some kind of, that's exactly what we did, two half direct scatterings. Using that we know one of them here and not the other, we can calculate A bar, B bar at t equal to 0 in terms of V. And same at final time, we know V but not U. By doing the direct scattering, we can calculate A bar, B bar in terms of this unknown U, essentially Fourier transforms.
The capital T is the same capital T that you introduced in the beginning?
Yes.
Capital T.
Capital T is the final time.
It's the same one as the one you introduced at the beginning?
Yes. Yes. Okay. Yes. Exactly. But the scattering process, so you're right, I should have put a capital T here. So we do two direct scattering, and we know how this scattering data evolves just by phases. Okay, imaginary phases. So we can match them, and we can get two equations for these two unknowns. And the equations are quite nice. They're in fact quite simple. So this is the procedure. You can calculate the scattering data at final time. You can calculate the scattering data at initial time, and everything is expressed in terms of the Fourier transforms, in fact, half Fourier transforms, Fourier Laplace transforms, these are details, of your unknown functions U and V. And when you match them by using the evolution, the trivial evolution equations of the scattering data, these ones, by matching the values at 0 and at capital T, you can get a closed equation for the U function. So the U function, I should remind you, is the profile. So it has a nice physical interpretation. It's a profile. And it's more or less what we are looking at, the profile at final time. So this is the equation you get. This is the Fourier transform. This is the full Fourier transform from minus infinity to plus infinity. This is the half from 0 to plus infinity. And this is the other half minus infinity to 0. Of course, U plus U minus is equal to U. It's full Fourier transform. Well, these kind of equations are well known again. So this is a single equation at the level of Fourier transforms. This is a so-called Riemann-Hilbert problem. Okay, because this is this plus this. So if I add 1, I can factorize it out, and I can rewrite it like that, because u plus plus u minus is u hat. So it tells you that you have two functions, u hat plus and u hat minus. You have some analyticity properties which are quite easy because it's just Fourier transforms. So for example, if k has a positive imaginary part, these things decays at infinity and so on. So you know in the complex plane, you know this function, it's a Gaussian essentially, and you have to factorize it into two blocks, one which is analytic in the upper plane and the other one which is analytic in the lower plane. This can be solved by using contour integration and Cauchy formula, and in the end, you get an explicit formula for the Fourier transform of your profile. So you cannot compute your profile in real space, but you get the Fourier transform, which is as good. And in the end, you need to integrate your profile over space. So you need to take the zero component of your Fourier mode. So you get an explicit formula. And from this explicit formula, you can plot things. So you can, so maybe, I still have a few minutes? Yeah. I will just explain the picture. So you remember, let's come back to physics. We wanted to compute the probability of having some current, some non-typical current going through the zero side. We're starting with rho plus and rho minus on the left, rho plus on the positive side. And suppose I want to look at the history, how does a non-typical extra current flow through my system, much more than the normal current just due to the simple diffusion. Well, in order to produce some extra current, which is quantified by this variable lambda, lambda is the Legendre, the fugacity of this current. What you need to create an extra current is first, if you want to have an extra current, it's good to use an initial fluctuation in which you have more particles behind and less in front, so that it will help to have more flow. Okay, if you have an initial fluctuation of your measure in which you have slightly an overshoot of particles in the negative side and an undershoot of particles in the positive side, then of course it will help you to force more current into the system. And then the system evolves, and in the end, at the final time, of course, because you had an extra current, you have depleted particles from the left. That's the profile at the final time. You have a shock, and you have an overshoot of particle on the right. So thanks to this procedure and solving these equations, you can really see what happens into your system. I'm not good enough to make movies. Of course, I mean, if I was, I would of course do it. You could see the wave, in fact, constructing itself, building up, going through the system and being depleted because you have pushed the current, the extra current through your system. So yeah, it should be possible to make a movie. Here, these are only static pictures, but with some imagination, you can see the moving, building up, okay? You can see that time slices of a movie at 0 and final time. And this is the extra momentum parameter that pushes your current. This is maybe slightly more arcane. Anyway, you can use this result to compute the large deviation function of your current through 0. And if you remember, yesterday I told you to get something much more complicated than that, but in fact which contain that by using integrable probabilities. So you really match between the microscopic calculation and the macroscopic calculation. But here, you only get the large time limit. You will never get a freedom determinant by this approach. You're already in the scaling limit. You're already in the saddle point limit. So somehow it's a kind of commutative diagram. Either you solve things explicitly, microscopically at any finite time, and then you take the scaling limit and you get the large deviation functions. Or you take the scaling limit first, it gives you the MFT equations. And if you solve them, you're able to find the asymptotics of your freedom determinants, more or less. So this allows you to retrieve some results that were obtained first by Derrida-Gershenfeld for the one-point current, and in more general case, and also for this tracer that I told yesterday that we did a couple of years ago with Takahashi Imamura from Shiba and Tomohiro Sasamoto, who was in Shiba but who is now in Tokyo. So the nice thing with this MFT again is that it allows you to compute the optimal profiles, so the history of the system. Deep inside, I have the faith that this could have been done by using Bethe Ansatz microscopically, but I have absolutely no clue how to follow the history by using Bethe Ansatz. It should be possible, but for the moment being, well, we are already happy that we could solve the MFT equations. So I'm going to conclude. I hope that I convinced you in this series of lectures that large deviations were important, that they were generalizing the ideas of free energy far from equilibrium, the ideas of entropy. And then once you know these large deviation functions, you are able to compute the statistics and the fluctuations beyond hydrodynamic approach of some interesting variables like the current or profile and so on and so on. Of course, there are some general results using Galavotti-Cohen or Dzerzhinsky, but these general results are very general and they don't really tell you how to compute things. They are kind of checks and identities that are always true, like thermodynamics, but they don't allow you to compute these free energies. You can do it by addressing the problem at microscopic scale, by solving interacting particle processes using combinatorics, integrability, whatever. And then you have to go to large scale. And there are many techniques, matrix ansatz, Bethe ansatz, integrability, and so on. Or you have the other point of view, which is to look at hydrodynamic limits by adding some noise to at least have access to the fluctuations. And then you enter this field of the macroscopic fluctuation theory, which is nothing but optimization procedure. It's really optimal path calculations. So it goes back, in fact, to Euler-Lagrange and to, yes, variational calculus. But unfortunately, yeah, it was not so easy to find explicit time-dependent solutions of the MFT. But suddenly, within the last year, in different domains, weak noise KPZ, it was Kragenbrink-Dussal, Bettelheim, Smith, Mearson, and Grabsch et al. For using a different approach for KMP and ZEP, and the thing that, of course, I told you that we did at the same time with Tomohiro and Hiroki, Tomohiro-san and Hiroki Kun. And these exact results that I showed you are based on inverse scattering, which was initially developed for dispersive hydrodynamics, NLS, and equations like that, integrable equations. And again, this is a kind of leap of faith, but I really do believe that inverse scattering at classical level should be very useful to analyze these macroscopic fluctuation theory equations, these nonlinear equations that describe large deviation for particle systems. I think it's quite promising, but indeed, and that's your question that you just asked a few minutes ago, the precise relation between microscopic integrability and these contour integrals and Bethe Ansatz and Tracy-Widom machinery and the machinery of lax pairs and macroscopic integrability and Gelfand, Levitan, Mazur, Marchenko is not clear. There must be a lot of things to understand. And of course, there must be other models that one could solve, other boundary conditions, and well, there's still work to do. Okay.
Thank you very much. Questions?
Everybody's hungry.
So I had one about the sort of connections that exist between this theory of large deviations and experiments. I mean, are there close types, or are these such idealized systems that they're not so useful?
So, yeah, it's a very important question. One possibility is these large deviations in small systems, like these experiments on RNA that I showed you, small with 100 degrees of freedom, things like that. If you know the large deviation function, by Legendre transform, you know the cumulant generating function. So you have an access, analytical access to higher cumulants than the second. Not only the variance, but the so-called kurtosis and the third cumulant. I forgot the name, they have names, asymmetry, parameter, and so on. And for the exclusion process, there is a group, for example, in Stuttgart, headed by Christian Beschinger, where they have measured experimentally the third and the fourth cumulant, for example. Complete large deviations are probably hard to access, but higher order fluctuations are possible. There is also a set of experiments, rather not exactly on ZEP, but rather on weak noise KPZ, which was conducted in Tel Aviv. And Baruch Merson, who's the person who works on this field, I cited him before, did the calculations. And people are looking at polydispersed colloids. I can find you the precise reference. And there was a match between some analytic calculations. But essentially, one thing one has to admit, this is not very large deviations, very far from equilibrium, but it's a beginning. So people are trying to find some model systems like in colloids where they can test these ideas in vivo, I mean, in the experiments.
Could we imagine in the other side, for example, for the Big Bang or something like that?
The Big Bang, that's a rare event.
No, but we know it's out of equilibrium.
Yes, so
and
I'm joking, but your question is perfectly serious, in fact. And I do have some colleagues doing astrophysics and, inflation models and so on and so on. At least at the mathematical point of view, what I told you about is nothing but instanton theory. In fact, in a field theory, we are computing instantons, several points of some action. And some people are trying to use these large deviations. I have a colleague called Francis Bernardo, for example. So he's not exactly Big Bang. I mean, he worked on the Big Bang, but for example, he's interested in some shapes of galaxies and things like that, where he tries to apply instanton theory. Because they have Borger's equations, in fact, that arise naturally. Chandrasekhar was one of the big guys who developed these Borger's equations for galactic aggregation and so on. And there are some kind of noise in the initial condition, and they want to see if there's some signature of these kind of things in their observations. So in fact, it's a good question. As you perfectly know, I'm not at all a specialist of this aspect, but it's not.
So I think everybody will agree that this has been an excellent series of lectures, and we very much appreciate all the effort you put into it.
Thank you for the invitation. It was a pleasure.
Thank you.
Thank you.